Signals and systems, Laplace transforms, problems, first part. Series on signals and systems, lecture number 4.13. In this session, the focus is on problems based on Laplace transforms. Some of these problems, they are set around causal periodic functions, and remaining are based on properties of Laplace transforms. Let us move further and see the problems and their solutions. Before going to the problems, let us consider the definition of Laplace transform. While solving the problems, while finding results to the problems, presence of definition of Laplace transform in the background is quite useful. So, we consider first definition. Two types of transforms are there. Bilateral, it is hardly used. Another is unilateral. This is the one which is widely used. Unilateral one is also called one-sided transform. Bilateral one is called two-sided transform. Bilateral transform of a time domain signal f of t, it is indicated by capital F of S. Here S is transform variable. It is complex frequency equal to sigma plus j omega. Omega stands for real frequency. As already mentioned, S stands for complex frequency. Sigma, it denotes attenuation. F of S is integral minus infinity to plus infinity f of t e power minus st dt. This relation gives bilateral transform. If the requirement is unilateral transform, then simply change the lower limit on the integral sign to 0 minus. Except this difference, both are same as far as forward transform is concerned. Now, here reverse transform is also given. It can be used to find time domain signal from frequency domain signal f of s. F of t is equal to 1 by 2 pi j integral sigma minus j infinity to sigma plus j infinity f of s e power minus st ds. This is a reverse transform, but this is not of much use or used. Anyway, these are the defining relations pertaining to Laplace transforms. Before moving further, one or two important points regarding transforms. Laplace transforms are useful to transform integral convolutions and differential equations into algebraic equations. Notice algebraic equations are always easy to deal with when compared to integral equations or differential equations. Algebraic equations are always less difficult, less complicated when compared to integral or differential equations, as Laplace transforms are able to convert integral and differential equations into algebraic equations. These transforms, they are able to provide some comfort, convenience by making our work less tedious and less cumbersome process. It is a more general form. Laplace transform is a more general form, and Fourier transform is just a special case obtained by letting s equal to j omega. Now, problem. Here is a problem. Derive Laplace transform for the given waveform. Notice it is periodic and it is existing only on positive time side. Hence, it is causal periodic signal. Shape is sinusoidal, therefore it is causal sinusoidal signal. One can notice it is half rectified sinusoidal signal. So this signal can be called causal half rectified sinusoidal signal. To find Laplace transform for this signal, we have a formula, standard formula f of s Fourier transform of the signal is f naught s of s divided by 1 minus e power minus st. Here capital T stands for time period of the periodic signal, and f naught is Laplace transform of first cycle of the signal, this one. Let us denote the first cycle of the signal by f naught of t. Then f naught of t, it can be expressed as a sin omega t when t time is in between 0 and pi by omega, and it is 0 when t is more than pi by omega. So here it is 0, here it is sinusoidal. F naught of s, which is Laplace transform of f naught of t, we are applying definition of Laplace transform. It is equal to integral 0 to pi by omega a sin omega t e power minus st dt, which is equal to a by 2j integral 0 to pi by omega e power j omega minus st minus e power j omega plus st dt. So integration results f naught of s as omega 1 plus e power minus pi s by omega by s square plus omega square. Note here a is amplitude of the sinusoidal signal. Now we know that f of s f of s is Laplace transform of the complete signal, causal half rectified sinusoidal signal. It is f naught of s by 1 minus e power minus st. This is the formula for Laplace transform of causal periodic function. F naught of s is known. Substitution and a little bit of manipulation gives us f naught of s as omega by s square plus omega square multiplied by 1 minus e power pi s by omega. Now we consider another problem. This problem is also based on causal periodic signal. Here signal is rectangular pulses. Several pulses are there. Notice that all these pulses are on the positive time side. One can notice periodicity. Therefore, it is a causal periodic signal. As we used the formula f of s equal to f naught s by 1 minus e power minus st. Here also we use same formula to find the Laplace transform. So let us start. Problem is derive Laplace transform for the given waveform. The given waveform is causal periodic one. The formula requires us to find f naught of s first. So first let us define f naught of t, which is time domain signal corresponding to f naught of s. F naught of t is a u of t minus a u of t minus lambda, delta. Notice the signal, the first cycle of the signal, it is from 0 to t encircled by the pen, and the starting point is 0. The pulse is there up to delta. From delta to t, it is 0. So 0 to delta pulse is there. Delta to t, it is 0. Now focus on 0 to delta. Here is one step function. At delta, another step function. Once we identify the rise and falls as step functions, we can express f naught of t as combination of two step functions, a u of t minus a u of t minus delta, this one. From delta to t, of course, it is 0. Now Fourier Laplace transform of f naught of t, that is f naught of s. It can be found by applying Laplace transform to f naught of t. Of course, one has to apply the transform to the signal that is there between delta and t also, but it is 0. So we need not bother about it. Laplace transform of step function, we know it is a by s for a u of t, and it is a by s e power minus s delta for a u of t minus delta. It gives f naught of s as a by s 1 minus e power minus s delta. Once f naught of s is known, the desired transform of the causal rectangular pulse train can be obtained by using the formula f naught of s by 1 minus e power minus st. Substitution results in f naught of s as a by s 1 minus e power minus s delta by 1 minus e power minus st. Now we consider another problem. Derive inverse Laplace transform of the given function f of s equal to logarithm s plus a by s plus b. Earlier two problems are finding forward transform. Now it is inverse transform. Solution. F of s is given as natural logarithm s plus a by s plus b. This can be written as logarithm s plus a minus logarithm s plus b. Now differentiate this expression both sides with respect to s. df by ds becomes 1 by s plus a minus 1 by s plus b. Now take inverse transform both sides. Inverse transform applied to df by ds gives us e power minus at. This is inverse transform of 1 by s plus a. E power minus bt. This is inverse transform of s plus b. Now, according to frequency differentiation theorem, minus t f of t for this Fourier Laplace transform is def of s by d, or f of t is equal to minus 1 by t inverse transform of df by ds. But we know inverse transform of df by ds, this one. The substitution of this expression here for f of t, in the expression for f of t, one can get f of t as minus 1 by t e power minus at minus e power minus bt. So this particular problem is an application of frequency differentiation theorem. Notice here we have not used the defining relation of inverse transform because it leads to a very complicated, difficult procedure. Another problem, derive inverse Laplace transform of the given function. f1 of s is equal to s natural logarithm s plus a by s plus b. Notice this problem is very much similar to previous problem. Only difference is s is present here in the problem. In the earlier problem, it was not there. Now, solution. Let f of s is natural logarithm s plus a by s plus b. Its inverse transform is f of t equal to minus 1 by t e power minus at minus e power minus bt. This has been found in the previous problem. It is brought from the previous slide, but with 0 initial conditions according to time differentiation theorem. For Laplace transform of df by dt is sfs. So inverse transform of s f of s becomes equal to d by dt f of t, but f of t is available with us and it is substituted here. Thus, inverse transform of S logarithm S plus A by S plus B. It gives d by dt minus 1 by t e power minus a t minus e power minus bt. So a little bit of differentiation gives us inverse transform of S natural logarithm S plus A by S plus B as 1 by t square e power minus at minus e power minus bt plus 1 by t a e power minus at minus b e power minus bt. After doing several inverse transforms, now we consider a problem which is based on forward transform. Derive Laplace transform of the given function. The function is named as f1 of t. It is equal to sin omega t by t u of t. Solution. Let us suppose f of t is sin omega t u of t. U stands for unit step. Notice f1 of t is f of t by t. The transform of f of t, let us designate it as f of s. It is equal to omega by s square plus omega square. This is a standard relation or result. Now, according to frequency integration theorem, Laplace transform of f of t by t is integral s to infinity f of s ds. Thus, Laplace transform of sin omega t by t u of t becomes equal to integral s to infinity omega by s square plus omega square. Integration and substitution of the limits results in cot inverse s by omega. Now we come to an end of this session. Before closing down, let us recollect aspects of problems that are dealt in the present session. Two problems are based on Fourier transforms of causal periodic signals. Some problems are based on finding inverse transform, and one problem is based on frequency integration property to find Fourier transform. Hope this session is useful to you. We meet again in another session soon.